Okay, our next speaker is Claudia Felser, the director of the Max Planck for Chemical Physics of Solids. And I think there is no one in the world who has synthesized more topological materials. Now she's focused on structural chirality. She's very motivated about it, and she's going to give us 2 lectures on chirality, magnetism, and topology. So, Claudia.
Yeah, first of all, I have to say I can not say who has the most materials discovered anyway, so whatever. So I first want to thank the organizers for sure for getting invited again. I pray every year, you know, do I get the invitation? Do I get the invitation? Can I come back to San Sebastian? And first of all, so you will enjoy the time, even sometimes it's raining, but it's not too hot, so this is a positive side, okay? And I have to thank for sure Charlie for giving this fantastic introduction, so therefore I can go over the first slides a little bit slower, and I'm happy that he at least came to the quantum hall effect. So anyway, so now you can relax, you know, so now you know all the theoretical background and all the formulas, and so I simply bombard you with a few materials, but it's simply a pleasure for you, most of you. Are there only theoreticians? Are there some experimentalists here? Okay, there are a few experimentalists, okay. So anyway, so to see that this come to real life, and so we all have our history, and I worked on many different areas, and I think theoreticians always have predict something, and then you make the materials and you never see what they predicted. But this is different in the world of topology, and this is different because of this very simple concept, I would say, and it's amazing. So I want to give you also a little bit the impression that there's a lot of application beyond the quantum computer and the big things, you know, and I'm quite sure that we soon have probably materials which can convert energy more efficient than normal thermoelectrics by simply using the concept of topology and the stimuli we have, magnetic field, and all these other things. So give you a little bit an impression, and I'm still thinking we are only at the top of the iceberg, because there was a nice meeting also at the APS meeting last year where they even reach out into the area of biology and chemistry. And I would say, honestly, I was always a little bit like lonely in the Max Planck Society because I'm a solid-state chemist, you know. But now I have many friends. Even high-energy physicists talk to me because they know, oh, she's doing something interesting. And now the biologists recognize, wow, topology. And their theoretical physicists turn into biologists. It's not the biologists, and they come up with concepts, maybe even explaining how the cell and biology function with the same concept, really with the same concept we heard from Charlie. So I think it's amazing. So we are still seeing only the top of the iceberg, and you should even think about other disciplines. And suddenly people from biology institutes come and, oh, you're doing topology. Anyway, so it's a magic word, and I think there is still a lot to discover, and you have seen the very nice explanation how the transformation has to work. And I want to show you simply the nice animation. Even you got already the explanation because this was done by my designer. So I transform now not a coffee pot into a donut. I take a different transformation. Anyway, so luckily you came to the quantum Hall effect. I would say also I still think that now looking backward, so if you always look backward, you have a different perspective. The quantum Hall effect was the starting point, more or less, where nobody saw, I think, and even Klaus von Klitzing, I remember a few years ago, before the big boom of topology, also said, yes, I did the quantum Hall effect, it's some exotic blah, 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 no impact, blah, blah, blah. Oh, then the kilo at least, but I would say, now, looking backward, I simply think it's amazing. Then you see, if you see the quantum Hall effect, this fantastic measurement, which are very precise, and you need a high magnetic field and low temperature, but to get those really nice topological properties, which were nicely explained by Charlie. So then you see nowadays with graphene, you see it even at room temperature, the quantization. So it's already showing that this is less exotic than it is. And then you even can understand, looking backward, if you read the old paper from Haldane, that what you can do in a very high magnetic field, then my materials perspective, why I'm so amazed by this paper is now, why did nobody think earlier that you can make a magnetic material, simply do a magnetic material, and you might get it without a magnetic field, which is a basic idea from my perspective behind this interesting paper to see the quantum anomaly Hall effect. And then the smart idea that you can have all this topological materials based on the spin-orbit coupling, so it's a natural, in some sense, consequence if you see it from the materials perspective. Anyway, so the proposal here was the graphene, which is a light element with smaller spin-orbit coupling. But I think it's amazing that the boost came suddenly because of one paper, so which was, and some other papers were totally hidden in the background. Okay, I think it's nice because I want to simply mention, and this was also nicely already mentioned, we need translation symmetry, and so for here no chemist, but I have to tell this also. So I would say I learned a lot from Roald Hoffmann in this sense because he had also very simple models. You could do the same model by using simply hydrogen atoms, and I recommend for people who wants to understand in a simple way also how to come from molecules to bands to this paper, and he has written a lot of papers where he discussed symmetry, and topology we learned is still based on symmetry. So many of the ideas to discover the materials came from these ideas in the background. Anyway, so therefore I think one of the magic materials still is the graphene, which so you can start simply, we had already double bonds and single bonds. It has a very simple pattern. And then if you go and add translation symmetry, because this is simply a condensation of graphene, so it depends strongly on this double bonds and single bond and this aromaticity here in the ring of benzene. So if you go then to solid, you gain this translation symmetry, nicely explained already from Charlie, so I don't have to talk too much about this, but you have here a very nice simple band structure where you have this nice crossing points, and I come back to this when I talk about Dirac semimetals, which gives very special properties. So I would say also what is the impact of topology is that people in the past, also like me, I did density functional theory calculation. We simply did some calculation and then we calculated with the Kubo formula or something a number, okay? But now we really shine light also on this pattern here. We shine light and suddenly we look for features in the electronic structure, band structure, like this crossings and other flat bands and so on. So we get much more information out of this black box. You put a structure in a computer, the black box has something in the computer, and then you get a number out. But now by interpreting even all these interesting features, we see nowadays much more. And I already can say that there are, if I have a crossing point, for example, in a magnetic material at the boundary between the occupied and the unoccupied state, I would immediately say, let's measure the Nernst effect. So this will lead to a very large, because we have a large Berry curvature related to this crossing point, and we see interesting properties. Okay, so as I said, so normally we had all the spaghettis here, this band structure, and now we have learned already much more to look for features in the electronic structure, for, as I said, flat bands and this crossing points in the band structure, and Van Hove singularities, and we can connect this very often also with properties. But we also look for surface state, like Charlie edge states and surface state get meaning, and the Berry phase and the phase of the wave function. This, I think, are also very important aspects, I would say, which came into the game from topology. And I foresee already that this can have much more impact also to other areas of science. We can have surface science. Can we do something in surface science where people use it for catalysis, for example, the chemists, if we have this topological projected surface states, or can we do something with the phases, the Berry curvature, beyond even the Nernst effect and so on. So I simply want to advertise this to a lot of nice application to come. Okay, and we deal with very simple definitions like insulators and semiconductors. So we have occupied states, unoccupied. We have a nice band gap, but we have now to look for the transformation of the gap, as we learned in the context of topology, we have metals and semimetals, and now I want to show also that you can define all of this on the viewpoint of topology. So simply by starting with the semiconductor, now bringing this to real life is like, as I said, so the nice prediction from Charlie with the graphene and the spin-orbit coupling, and that this could be leading to a quantum spin Hall effect, is like looking for something which has a valence band, a conduction band, but has this band inversion, because we learned already we have to have this transformation, so that we have this crossing point, this topological critical point. And so if you go and look into the, for binary semiconductors, so you see here's the energy gap and the lattice constant, and so there's already, this was known before the paper even of Charlie, so that you have this semiconductors where you can systematically see that the gap has something to do eventually with the lattice constant, because it has something to do with the bonding interaction and maybe other tuning parameters. But you see there's even a minus gap, so there's a negative gap. So this was already existing, that there were binary compounds which have an inverted band gap. So they are distinguished from the other compounds. Okay. So, and this is the story of topology if you translate it in a simple band structure language where we are looking for. So we have a valence band, a conduction band, and a band gap. But if the bonding becomes weaker and weaker, so the energy between the occupied and the unoccupied bands are becoming smaller, and you can have even a area of where you have the overlap between the conduction and the valence band. And this again brings me back to my old days where I learned band structures from somebody who comes from organic chemistry, Roald Hoffmann. So you have this forbidden crossing, and depending from the symmetry, at this time we were mainly looking what is the symmetry of the bands, but now we are looking for the topology of the bands. So is this crossing allowed? Can they cross here? Or do we open up a band gap in the band structure? And this is the case if we have heavy element compounds and certain symmetry. So we have spin-orbit coupling, and then we open up a band gap and we get a topological distinguished semiconductor from the normal trivial like silicon. So we have this with the inverted band structure, and this leads into this topological surface state. Charlie already discussed the edge states. So they are topologically distinguished in the electronic structure, like we see here, the donut and the pancake. Okay. So, and this means that here we have a crystal. If you have a crystal, I grow my single crystals, and this is what I do. Okay, so the crystal is really an insulator or semiconductor, and here we have this interesting spin polarized surface states where the spin and the momentum is locked on the surface of the material. Okay, so, and this is very nice because you have this, if spin and momentum is locked, we have this protected surface state, so they cannot be backscattered. So theoretically, we should have fantastic spin polarized currents, which would be then even very, very nice and interesting for electronics. And people, the first proposal here was also that people thought we have a problem if we make computers, so to connect the different parts of the computers, the interconnects, and if you have this really highly conductive, even spin polarized currents, you might have a totally new electronics area. Anyway, so now we know from all the materials in so their database, this where, especially in inorganic chemistry, this doesn't exist in organic chemistry if somebody wants to work on organic. So the inorganic chemists, if they make a new crystal structure, they put it in a database. And this is nice for all the people now working on topology, because based on this database, you can now do band structure calculation, the single particle pictures, and you make all your treatment, and then you can learn that from all the 250,000 compounds which we know, that at this time was 25% around is topological, and even we are looking now for magnetic materials which are topological, but now it's more or less everything is topological. If you allow to move the Fermi energy around, okay, which means we can dope, if you allow to dope with electrons and holes everywhere, so everything is topological. So there's nothing left, and if you even think of, about going a little bit beyond, which means I think we simply have you can say, so it's an inflation. What is the impact anyway, but I still want to show and to remind us, really, we now have to really look for the features in the electronic structure, because we can still, I'm quite sure we will have soon more and more application related on the topological properties, because the nice thing is now we move a little bit, we dope a little bit around, or we see suddenly, we see really materials where we have mean free passes, which are micrometers and millimeters long, you know. So the mean free path, for example, in my tungsten phosphide 2, I don't advertise graphene, okay, so it's larger than my crystal, okay, size. Or we see giant Nernst defects, and I think even we can rethink thermoelectric materials if we take all these special band structure features into account. Okay, so you simply can go to the web page, the topological quantum chemistry web page. You click here your elements, and then you get what you learned already, the topological indices. So Charlie also introduced them, and you learn whether it's a topological insulator, a semimetal, or whether the material is trivial. There's still trivial materials by simply taking this single particle picture into account. And I think the next step then is the change what Charlie already said. So we have to go to correlated system, and I think many people are working on this. So because you really have to still treat oxides with a grain of salt, and so because they are oxides, many people are super excited about oxides, but you have to go here beyond the single particle picture. And I still think in oxides we probably find a topological insulator which has even a larger gap and is less sensitive to disorder than bismuth selenide, for example. Anyway. Okay, so then you can measure the thing. So we know we have insulators. So if we measure insulators, we see if we measure the resistance versus the temperature, it becomes larger and larger with at low temperature. Because we have this electron gap here, and if we need a thermal excitation to bring electrons to the conduction band. In metals, we see this typical behavior because we have a lot of electrons in the bulk. And in topological insulators, so people think that this is a typical behavior because you see at very low temperatures a plateau. And you will see it in eventually also our measurement because of the surface state or the edge state. So, so to simply tell you also how do you practically do it, it's not like magic, and yes, students who are doing this, so you can talk to Narayan. You take your crystal and you put it on some of the puck, and you might see here that you make the contacts, and then so most of the time you measure Hall. It's the same measurement as you would do if you would see the quantum Hall effect, so you don't need a special equipment. This is simply for the theoretician also. So you measure the simple resistance here, and you measure it in a magnetic field. So this is what you can distinguish even in semiconductors, very typical. Then you can see even what are the charge carrier concentration and so on from this measurement. But you see sometimes also wiggles here, and then you might think it's impurities, but this is very often in this material. We see very nice quantum oscillation from which we then even can make a conclusion simply by simple transport measurement how the electronic structure looks like. So we don't need even Ingeris or photoemission or some complicated measurements, because very often we get this information. And it's amazing, before I never did this, you know, now since there's topology, so all my crystals suddenly have this quantum oscillation, because this is already very nice, because so we get much more information out. So then you can think, okay, if carbon is not the right element because it's on the top of the periodic table, what can we think about? So we need more heavy elements, and this was exactly what the people did after this nice publication. They thought, what are the heavy elements? But unfortunately, most of the periodic table is metallic. So first we thought metals are boring, you know. I like metals too, but anyway. So or they are gas, like you have chlorine, bromine, and so on, or even this helium and so on. So then it's really difficult to find a heavy insulating element which would have fit to the topological insulator story. So candidate materials are tin here in this area, okay? So nowadays we know you could make strained alpha tin, or I think bismuth a little bit tuned can show more or less every property too. Anyway, but the first idea then was, so if you start with bismuth, you alloy it with antimony, and but then also, I would say this was really the idea of Bob, to go to a famous thermoelectric material, which exactly was this first and still one of the best topological insulator. And for me, it's always amazing that that series is so fantastic. So you do a calculation, you know, with the surface, calculate the properties of the material, and including the surface, you make a slab calculation, and you really see whether there's a surface state or not. Okay, so this was amazing. So sometimes we didn't know, for example, if you have two band inversion in a band structure, so benign, as we did the calculation and we didn't find a surface state, we were totally disappointed because this was unexpected. But it's really true, you know. It's for me amazing that if you see the surface state is then also there. It's exactly what the series, a simple model, draw the simple surface state. They are really in reality. This is a calculation, and this was the first measurement from Hassan's group. Still, the samples were not so good, but so this is very promising. And I'm 100% sure there are more hidden, really, really very good topological insulators in the family of oxides. But therefore, I try constantly to motivate. But most of the time, if you do the simple band structure calculation, the oxides become metallic when they are insulating. So I simply go to the database and say, oh, it's a yellow powder. So Maya, nice prediction, but it's a yellow powder. This means it has a quite big band gap. Okay, so we have to have a better treatment of oxides. Okay, yeah, so then it was clear. So here are the candidate materials, because these are the negative band gap materials, the inverted band gaps. And this is now a little bit history how I came into this field. So because I was invited to a meeting where Shushen Zhang was, and this was just after the publication of their proposal that one should go with mercury telluride, and Lawrence Mohrenkamp already had mercury telluride and very nice quantum Weyl structures in his shelves in Würzburg. So, and these are two elements, okay? So we are going from one element to two elements. And this is also the nice story of topology, because I remember when I started with Ole Andersen in his group, he said, oh, Claudia, this chemist always comes with 2-element compounds and 3 elements. Okay, the high TCs are quite horrible already, but you know, can you come with something which has only 1 element? In topology, it's different, no? Charlie, now we can come with 3 elements, we can mix all the elements, and still everybody's happy, okay? So I think it has also led to that we recognize, so we can go from 1 element to 2 element. So, and then, my most favorite class of material were the so-called Hafeusler compounds, which are like you can have silicon, then you can have gallium arsenic, so like what Charlie Marcus likes, okay? The binary semiconductors, and they think they are doing ternary if they add a little bit of nitrogen into this. But then you can go to 3 elements and make semiconductors, and this was my concept, because here you can even make magnetic semiconductors much easier. Sorry. And so it was obvious. And Shushen was very fascinated, because that we can make many more compounds than mercury telluride. So we simply can have exactly the same band structure as normal semiconductor silicon with 3 elements, many of them, and we can have inverted band structure with a negative band gap with 3 elements. But the nice thing is, in this family of materials, which is a non-centrosymmetric structure, these are also superconductors if they are not magnetic. So we are just growing with Lawrence Mohrenkamp now, yttrium, platinum, bismuth, with the maybe hope, okay? With the hope. Oh, I'm not so good in. With the hope that maybe so one can find in this material, it could be a material for eventually Majorana fermions or something else, okay? So going to 3 elements, okay? So simply, so this is like what I said, Charlie likes gallium arsenic, and some people even tried then to make it magnetic by doping it with magnetism. But if you distribute these magic numbers of valence electrons over 3 elements, you have many, many, many more combination possibilities. And this is also famous thermoelectric material. So there is a connection between topology eventually and thermoelectrics, a general connection. So this was also one way we found many new compounds by simply looking for famous thermoelectric materials. And all these famous thermoelectric materials, scudorodides and so on, are very nice topological materials. And some are also interesting in the context of correlation, because, for example, some of them, like the scudorodides, are also superconducting and they're quantum systems. So I think, but therefore they are also not so well studied yet. Okay, so but then we thought with Ben-Hai, okay, so why not thinking about metals and thinking about, so because therefore there is this inflation, if you think, so gold is a very nice metal, and everybody says, okay, gold has this very nice color because of the so-called inert pair effect, so that the 6s electrons are contracted due to relativistic effects of the 1s electrons, so they are at lower energy than the 5 and the 4 relatively compared. And this is one of the, for me, big reason why all this heavy element compound have a topological band inversion, because the 6s electrons and the 5s electrons are quite low in energy, so they overlap then with the p electrons from the valence band, the conduction band, and then you get easily this band inversion, which you see here in the band structure of gold. So if the Fermi energy would be here, you would even have nearly a band gap in gold. But this is 1 electron. We could have done also platinum, but gold was a better sounding title. And platinum is the best catalyst on Earth. And so 1 electron, no, 1 electron less, sorry. So if you calculate here then the Berry curvature, you see that gold is quite good concerning the Berry curvature, but platinum is better. But platinum has many interesting properties which were known before, like it has a very good classical spin Hall effect, you know. It's still one of the best. And all these properties are related to the Berry phase and the Berry curvature, so I think it's interesting. And then we looked really for the surface state of gold, so people thought it's a Shockley type of, and even Shockley was mentioning that if you have 2 bands with different parity crossings, you get a Shockley state, but here it looks a little bit strange if you do the calculation, but it's really a topological surface state in gold, and we really could show even here's a Fermi energy with 2 photon electron spectroscopy that you have even this gold, metals can have this very nice, typical for topological material a surface state. Okay, so you can say it's not a gap, so we cannot take so much advantage, but the spin Hall effect, for example, or some other properties of surface properties, even if it's not, protection is not as nice as in the topological material, I'm still convinced that it has some impact on surface science. Okay, and as I said, this is why we love this kind of elements if you're thinking about topological materials, because they all have this inert pair effect, so the reduction of the 6s and 5s orbital to lower energy that leads then to this band crossing in the electronic structure. Okay, so we have now already discussed a little bit that we can make insulators, and there's still some need for insulators. So Maya is even thinking, I'm not sure whether I'm allowed to say this about organic insulators, going back to organics, okay. So we have very nice metals, and I think there's already still to do, but there are also nice semimetals and semimetals, so this electronic structure, which I think, yes, which has this band structure like graphene, is not so rare, because if you have 2 atoms in a unit cell and fold back your bands, then you get always this linear dispersion. And this linear dispersion is responsible for this long mean free path and this in this material, which might also have some impact for electronics. Okay, so we had this story, so going back here again, so we have this overlap between the conduction and the valence band, and then we have here this overlapping region. So if we draw this all in 3-dimensional, now we become more complex. So Charlie did 1 and 2-dimensional. So if we go to 3-dimensional, so we have not only here this crossing points, we have even a overlapping area, and this is very often you have this nodal line compounds, and this shows also very interesting properties. And then if this whole area is forbidden, so we can have the topological insulator with a nice surface state. But recently people were very much interested in looking for similar materials like we know from graphene. So if there are some certain rotation symmetries, for example, protected, then we can get the semimetals where we still have this linear dispersion and this crossing points. And so depending where in our electronic structure this position is, we can have Dirac or Weyl semimetals. So if you have simply the Dirac equation, you can have 2 different special solutions. So one is more with the higher symmetry, we have the Dirac semimetals. This is a 4-fold degenerated point then here, crossing point. And in Weyl semimetals, you have these points at low symmetry points, which means so it's also much more difficult to find because it's not so obviously very often to see in the electronic structure. And the relation is here, so you could turn a Dirac semimetal into a Weyl semimetal, so by lifting the degeneration of this 4-fold degeneration into 2 times 2-fold degeneration, which you can see here. So then the band structure would look like this. The bulk band structure would look like this. And here, so the nice thing is that you have this chiral crossing points in the electronic structure in this Weyl semimetals, and therefore I like to draw it with these different colors because this excites me, and Charlie already mentioned the chiral anomaly. So chirality in the bulk electronic structure, I think, is also, I think we can probably think even more about this, okay? So because here we have different phases of the Berry curvature at these different points, which is not the case in the Dirac semimetal. So we have chiral electrons in the bulk in this material, and this is why we can measure in Weyl semimetals this chiral anomaly. So we have here then in our crystal this different crossing points in the bulk electronic structure, which have different signs of the Berry curvature, and they look like a source and a sink of a Berry curvature. And then the surface state, which were predicted here, is this projection of this bulk electronic structure, which is this Fermi arc, which connects this projection of these 2 points on the surface. And this is, I think, a very interesting class of material. So, sorry, I think this is from a German, but I liked it because to show, so now, so if we have spin momentum locking in this material, so we can have these 2 different fermions. It's in a German article, sorry. So this is, we have what we have normally with the right and the left hand. In molecules, we have here with electrons, right and left-handed fermions. Okay, and I like it very much. So again, to make the bridge to chemistry, so it's because so I think the big interest of chemists is always, so if we have this chiral molecule. So carbon has 4 ligands, okay? And if the carbon atom has 4 different ligands, it's chiral, okay? Because then you have 2 kinds of molecules which are behaving like the mirror image, but they're like the right hand and the left hand, you cannot bring them together, okay? So, and so you are only made by 1 kind of molecules, but the chemists have problems. So if you do synthesis, you always get 50% of this and 50% of that molecule, okay? And the Nobel Prize last year was given to Ben List and Macmillan because they were able, with a chiral catalyst, to make only 1 kind of this. Okay, so this is very important, and nobody knows why we, as human beings, are made only by one kind of DNA and how it has happened. So nobody knows how the symmetry of life was broken so far, why we are only made by one kind of DNA and we eat only one kind of sugars. We cannot just one kind of sugars. And I like the analogy to the electrons, because we all know in physics, like the structural chirality in some sense is related to the electronic chirality. So we always make the connection because lattice and electrons and orbitals and so on. And this is very interesting. Okay, anyway, so this is simply, I come back in my second lecture to this idea. So what we now need to grow are these crystals, and these are simply giving you a little bit an impression. So we have many different growth methods, some where we simply take a tiny little crystal, so in a melt, and then we grow the crystal larger and larger and larger. This is a very well-controlled way to grow crystals, but sometimes we mix simply something together with some additional liquid. It can be also made by solids. So, and we hope crystals are grown. If the crystals have very simple phase diagram, but also one method is very nice also for 2D material is this chemical vapor transport. So you start with a powder and you have a transport agency and you grow some nice crystals simply to get you a little bit an impression. Okay. Good. Now I come, you know how we measure the things, how we grow the things, and how then we now have this database, what to do, which materials we do, and what are an interesting area to investigate is what Charlie already mentioned is this chiral anomaly, and which is a solution comes out of the Dirac equation, and this was developed for high energy physics so that you have a vacuum state fluctuation, so you can have a situation that you get an asymmetry between elementary particles and antiparticles. This is the other question, why is the universe mainly made out of particles? It's another fundamental broken symmetry where people are thinking about and are fascinated by. So there is the chiral anomaly is more or less a background which allows for the anomalous non-conservation. So if you have the situation that you have a special situation if you have the electric field and the magnetic field in the same direction, so you can have a situation that in the quantum world that the symmetry, this conservation law is broken, and that you can have an asymmetry between particles and antiparticles. And this was very nice prediction. And again, so despite of having prediction of materials, there are constantly new prediction also from Charlie and from Gershwin here. So some other people make very nice predictions. So what you should do with your material, and their prediction was that you can measure the chiral anomaly, which was all originally from high energy physics in a solid if you have a Dirac semimetal or Weyl semimetal. So, and you can measure it by measuring the asymmetry between electron and holes. So this is not okay. Yes, here with this, and there were many predictions here also at the beginning that it's possible to measure. So as I said, this is very nice. Despite of measuring our crystals, we have many ways also to have knobs to tune properties in these materials. So not only the magnetic field here, we can make light-matter interaction and so on. So, and you can change the temperature, which is important if you want to. And you maybe can even change the position of the electron, the magnetic field relative to the current, because the chiral anomaly, the prediction was to do this E dot B. Anyway, so we cannot now investigate particle and antiparticle, but this is a nice thing also of physics. So you don't measure the hen, you measure the hen as a quasi-hen, okay, which is sometimes also dangerous because then people can start to discuss, do you really measure the hen or what are you measuring, okay? So the quasi-particles, okay. Anyway, so so Weyl semimetals, because of this here of this Berry phase with different signs are very interesting, and there's a list of interesting properties you can measure, so this as a starting point. And so in general, which I want to show also slightly, they show giant responses to external stimuli, like what I showed you before. So if you apply light, chiral light, people did chiral light, they see very large photovoltaic responses, and I think also there nobody has done a systematic investigation. Can we compete with classical photovoltaic by introducing topological photovoltaic? I would not exclude it, because especially if you make more artificial material, and or the Nernst effect is giant. I think if you measure white semimetals, they show giant Nernst effects and other properties. So we want to see the Fermi arcs. We are interested in the chiral anomaly, and there was even related to the chiral anomalies that you can see some interesting features related to astrophysics, the gravitational anomaly, if you simply look for entropy. So if you don't do the magnetic field and the electric field in parallel, you do the magnetic field and the temperature gradient in parallel. Okay, so this is this chiral anomaly term, and the idea here was that if you have the electric field and the magnetic field here in parallel, that you see the prediction was a negative magnetoresistance effect. And this is always the problem with the quasi-chicken, you know. There are many other reasons eventually to see a negative magnetoresistance effect. So, but anyway, this was the prediction, and the first measurement were done on this direct semimetals, sodium 2,3 bismuth and gadolinium platinum bismuth. This is a Holster compound. So where they really saw this negative magnetoresistance, and but it became, again, it's a lot also in this field of topology. In the moment when you have a simple material, which is nice to tune, because you can go from lighter elements to heavy elements, so you increase relativistic effects, spin-orbit coupling, and they are quite easy from their electronic structure. So these semi-metals, when they were predicted, with this very simple structure, 2 elements, not too complicated band structure, and so on, this field of semi-metals were really, I think, boosted. And here we also made this material. Here has nice big crystals, and you can see nicely that they have really the electronic structure here in photoemission. The sign here for the Weyls are made artificially. This is not measured. Anyway, so you see this nice linear dispersion in these materials, and so we made all the crystals, and you see if you make the crystals, the binary materials, more heavy, so you see the band splitting becomes larger, and here the surface state is the calculation and the measured surface state. It's really amazing how nicely it agrees in this simple material with a single particle picture. And for us, it was really amazing, like all these materials we are now making, suddenly people predict material. So I think there was a time when people were talking about large magnetoresistance effect for spintronics, like Stewart became very famous because of this, and they had effect like 100%, okay? So it's a factor of 2, okay? But you see now in these materials, you see even much more giant effect, and nobody has measured this simple compounds, you know, because everybody measures only what there was some prediction, but here even at room temperature there's still large effects. So so you see responses now, and here you see these nice wiggles, which are the quantum oscillation from which we really can draw really the electronic structure of this material. But then if you apply magnetic field, and you see it ends always, the electronic structure is like a plateau. So it's also here in the semi-metals, the question what happens if you go higher and higher in a magnetic field. But you always see these very giant responses, okay? So you see also mobilities in all this material, which are known for a long time only for gallium arsenide, 2-dimensional electron gas, or then graphene, and now there's an inflation of materials. All the semi-metals shows this very giant mobilities. Anyway, so here we looked for the chiral anomaly, because here we made very nice nanoribbons to avoid all these measurement problems, okay, and we saw that the conductivity is negative, which means the resistance is positive, if we have the magnetic field and the electric field perpendicular, like in a normal Hall measurement, and then if you turn the magnetic field in the direction of current, you see a giant change in the properties which we think is a chiral anomaly, and which is here simply for the people who are interested, were proposed originally in high energy physics, but nowadays people try to prove the chiral anomaly with heavy ion collisions. So they think in 10 years they maybe can show the high energy version of the chiral anomaly, but it's already done if you want in white semimetals. But you can also do the same experiment and applying a temperature gradient, as I said, and it had the same effect, more or less, on the properties, which is in some sense logic, because the thermoelectric transport is related to the electric transport via the Wiedemann-Franz law. Okay, so we think also that this is a real measurement and no current jetting because it fulfills the Wiedemann-Franz law. And this, as I said, was done with these nanoribbons, because here you also see nicely again the quantum oscillation, and so we could really see in this material that we had the Fermi energy at the Y points. I think this is very fascinating, this fundamental broken, and I think one should even think more about more experiments and things relation. And nowadays, this was also done for other materials, like here for this bismuth antimony. You can see also very nice effects, even up to quite high temperatures. So also here you see the chiral anomaly and this term temperature gradient. This was work from Jos Heremans, and people did it now in many other materials, and it's very typical for this white semimetals and so on. Okay, this axial gravitational anomaly, and this was done in collaboration with is he there? No, it's not there. Anyway, and some people from IBM, and they are much better with the PR. You know, they made it. Even it started in our group with Johannes, so at the end it became an IBM experiment, but they brought it even into the New York Times. Okay, so I don't know when we have the break. Yeah, because I could make a break now. So the nice thing is, what I said, and this is simply as an idea, what I said is like, if you have a Dirac semimetal, you can strain the Dirac semimetal, you reduce the symmetry, you remove inversion symmetry, then you can turn a Dirac semimetal into a white semimetal. But the other way to make white semimetals is to break time reversal symmetry. And this is nice, because this is even a bigger field where I think there's still a lot to do, are the magnetic, because if you make something magnetic, every crossing point in the band structure is a Weyl. So you can really, there's an inflation. Okay, more or less every compound can be turned into, by doping the Fermi energy to the right position, into a Weyl. And this is really where you see you can have many interesting properties, despite of the chiral anomaly, which we showed also for some magnetic material, and the gravitational anomaly. But you can have also, I want to talk a little bit about the anomalous Nernst effect, because this is a way to directly measure also the Berry curvature and the anomalous Hall effect. And also there we find now suddenly in materials much higher effect than people thought are possible, you know, because simply by turning the electronic structure to the right point. And I would say this is after then the coffee break, no, because this is now a nice way to break.
Thank you.
Some point, I know it was kind of like you mentioned a couple of times also like the organic molecules idea. I'm just wondering if in this sense to find topological things in the organic molecules is kind of related to all these conical intersections that appear in this type of molecules, or what kind of topology do you mean in these organic molecules?
Yeah, so one thing is you can have crystals, and you have to have an assembly of molecules, okay, then you can get similar things, but it's, the other thing is that, yeah, how to, so one is in the other way, I would say, which direction, which I would think about, so people now thinking especially about the chiral molecules, and they think, so there are people coming up with the idea that there can be maybe a formulation of a geometrical phase which is different and distinguished from the barrier curvature. So we have an advantage with the translation symmetry, okay? So here they don't have it, but maybe it's a way to maybe help to understand maybe interaction between molecules and solids. And yeah, so the other one is maybe chemical reactions, because if you have then you have not K as a parameter, you can have the reaction coordinate as a parameter, and you see then also crossing points and topological transformations if you think about things like this. Okay, but I think there are even then I not stop answering the question. I think all the theoretical physicists now even thinking about biology, it's like you should simply Google it. It's amazing.
Thanks for the talk. So also about the organics, I mean, you mostly focused on the mechanism with spin-orbit coupling, right? So like, but carbon doesn't really have spin-orbit coupling. So how would that work in this framework?
So in the organics, sometimes, so I think you might have then to have metal organic things. So, but I simply think there's also kind of crystalline topological insulators. So I think there are also ways to have this phase transition, because the polyacetylene or whatever, the organic models are always done with carbon, you know, but it's true. If you need spin-orbit coupling, you have to make it heavy, okay? So, but if you can have conceptual similar things like in crystalline systems with different ways to do topology, you might even can do it with and I would say, so realizing like graphene, Dirac kind of electronic structure, which already has very interesting properties, you can do with carbon. You don't need spin-orbit coupling. But you know, this is like having many different knobs, and but there you can also have compounds which have magnetic ions and so on, or maybe even then going to hybrid materials like the perovskite, the famous solar cells now. The question is here, they work very well with heavy element compounds. Is maybe there also some importance of spin-orbit coupling and so on at work? But it's a good question, yes. But I still think thinking in new direction, combining symmetry and all these different knobs. So because in organics, and also if you combine inorganic, organic, sometimes it's easier to arrange the building blocks, okay? So because if we make a solid, we go to very high temperature, and we are very much related on thermodynamics, you know? So while if you go to lower temperature and have the building blocks also like this, which is also quite nice with this perovskite material, which have organic building blocks plus inorganic. If you can do it at low temperature, you can build it more like a Lego, you know.
But I mean, for this kind of class of materials, I don't know anything about organics, but usually molecules don't conduct, right? Or most of them.
Yeah. So you have to find the right materials. But you have also superconducting organics, you know. So I think one should not exclude this. So you can do conceptual different things. Also in biology, they don't care about conductivity. They simply go for the concept of phase transition from one topological phase to the other, even in hydrodynamics and stuff like this. So I think it's applying to really different. So you don't have to only have conductors and insulators, you know.
Thanks.
So we know that there are a lot of practical applications for the magnetoresistance of these kind of materials. Do you know of any such applications for materials showing or displaying chiral anomaly or gravitational anomaly or one of these?
So I think the chiral anomaly, I think, is in some sense related as far as to the photogalvanic effect and so on. And I think there you could also try to further optimize. There's this one experiment of Nugedek, okay, where they shy, because the point is simply this a little bit, Adolfo, I didn't see you. Okay. Anyway, so that they shine chiral light, and then they get a current in this, and they change the chirality of the light. I like this experiment, and I think Liang Fu is thinking about this, I think, very intensively. But I think that it's not as easy, you know. Everybody has a PPMS in the lab, you know. We grow the crystals, measure. We see the magnetoresistance effect, you know. And now we are doing thermal transport, which also goes faster, okay. So therefore, we do a lot of thermal transport to find a nice application in neurons. But I think the light-matter interaction is still more challenging. But I still think that this is a very nice field also where you maybe should do more systematic investigation to see whether there's a way to have application, because the responses are really big, okay? So the other thing is to turn the responses to the right energy level. So the nice thing of thermoelectrics is also because people have application for low temperature in outer space, people have application for room temperature, but people also, it's possible also to see effects at higher temperature. So anyway, this is another change. But there's a lot to do, yeah. Thank you.